Okay, now we're going to start talking about understanding the relationship between a shear function and a moment function. You might have already started noticing some things. So let's talk about it. Basically, what we're going to answer today is how are shear and moment related. And we're going to do that first by looking at a small segment of this beam. It's subjected to some arbitrary distributed loading. And we're going to take a tiny little segment right about here. And my segment is going to have a width of delta x. Okay? So on my little segment, I have on one side, I have a shear force with a value of V of X. And I also have, I'm going to write that down here, V of X. And I also have a moment with a value M of X. And remember, this is my width delta X. And delta X is so small that the applied load, distributed load, is constant. Over that width. Okay, so on one side, on the left side, I have a shear with the value V of X and a moment with the value M of X. And on the other side, I have a shear with the value X plus delta X, which is essentially my shear on the other side, V of X, plus some delta V. And it's not going to be equal and opposite because I have an applied distributed load going on as well. If there wasn't that applied load, then yeah, the shear would be the same. And I also have a moment with a value of X, M of X plus delta X, which is essentially M of X plus some delta M, some change in moment. So let's look at the sum of the forces in the y direction. I have V of X acting upward. Acting downward, I have W of X, or W, but W of X. Oops, downward, so negative. W of X times that width, because it's a distributed load. Right, I have V of X, I have this W of X. And I have my V of X plus delta V equals 0. So simplify that out. I have V of x minus W of x times delta x minus V of x plus, oopsies, minus delta V. So V of x minus V of x, that can go away. And if I solve for delta V, I get negative W of x times delta x. If you guys all took calculus, you might see where this is going, right? So if I divide by delta x, right, I have delta V over delta x equals negative W of x let's take the limit as delta x goes to 0, as that width gets smaller and smaller and smaller. And what I've basically just decided is the derivative of shear with respect to x is negative, is the distributed load function. And the reason why it's negative is because it's acting down, and I chose up as positive. So that's the only reason it's negative. So this means the slope of my shear diagram, or shear function, is equal to the magnitude and direction of the distributed load, of the applied distributed load. So if I want to know if there's a distributed load on it, I take the derivative of shear with respect to x, which is the length along the beam. Okay, now I'm going to do the same thing, right? I have V of x and M of x happening on that side. My width is delta x. On the other side, I have V of x plus delta V and moment of x plus delta moment, right? So now let's take the sum of the moments about this point is equal to 0. I have M of x acting counterclockwise, or acting clockwise, so it's negative. I have my shear force acting at delta x clockwise, so it's negative times delta x, right? My force times my moment arm. I also have this W of x resultant, right? W of x times delta x, and it's acting at a distance delta x over 2. Right, delta x over 2. It's just making that more visible. So I have the resultant, and this is acting counterclockwise, so it's positive. The resultant, W of x times delta x, and it's acting at a distance delta x over 2. That's multiplied. Why does that look terrible? I can ignore the shear force because it has 0 moment arm, this one. But also acting positive, I have m of x plus delta m. So again, let's see, I can cross that out. Now I've got delta m is equal to v of x times delta x minus w of x delta x squared over 2. Now, if I recall, delta V is negative WX delta X. So I'm going to replace part of that. So delta M equals V of X times delta X minus delta V times delta X over 2. Right. So that is going right there. And actually, if it's negative, then it would be technically positive here. So if I divide by delta x, I get delta m over delta x equals v of x plus delta v over 2. Okay, again, I'm going to take that limit. Remember, we all love limits. As delta x goes to 0, as delta x goes to 0, this change in shear is going to get smaller and smaller, and it basically equals 0. So this means I get the derivative of the moment with respect to x is equal to the shear function. Right? Go back and look. You'll probably notice that on the shear and moment functions that we did as examples. That means that the slope of the moment function is equal to the shear function. Right? It's kind of like when you guys all learned physics and suddenly you noticed, hey, the derivative of the velocity is the acceleration, and the derivative of the derivative of the position is equal to the velocity, right? Same thing, the derivative of the moment is equal to the shear. The derivative of the shear is equal to the applied distributed load. Right? So let's summarize that. Right? The derivative of the moment with respect to x is equal to the shear function. The derivative of the shear function with respect to x is equal to the applied distributed load, including the direction, which is why it's negative. Conversely, right, now let's switch from differential calculus to integral calculus, right? Converse also true. If I take the derivative or if I take the integral of the shear function, right? If I take the integral of the shear function over that length, delta x, I get the change in moment. So if I find the area under the shear diagram over a certain length, it'll give me the change in moment over that length. If I take the integral of the applied load over that length, I get the change in shear over that length. The change in moment over delta x and the change in shear over delta x. Between 2 points, delta x, you can find the change in moment or the change in shear by integrating. I'm missing that negative. Of course. Oh, it's all messed by integrating the shear and applied loads, if it's distributed load. So now we're going to work on building some shear and moment diagrams and building them, and it'll illustrate these points visually for you. So if we want to draw a shear moment diagram, right, determine our support reactions, determine shear and moment functions like we talked about previously. Along the length of the beam. Right. Follow the procedure that we previously discussed, and then you're going to plot them. That's really the biggest difference, is we've already developed them, now we're going to plot them. On a chart with x-axis being the position x, position along length, and the y-axis being your shear or your moment. Don't draw them on the same plot. I mean, you can, but maybe have two different scales. It doesn't really tell you much to have them on the same plot. I guess, yeah. I don't know. Maybe if you're running out of space. Right? Shear and moment diagrams are extremely important for developing your design, locating maximums, minimums, and where you are decreasing the applied load. They can also be used for building envelopes, or not building envelope, for taking the envelope of your moment function or your applied moment for different load cases. They're very useful, and they are used by engineers regularly. So, okay, now I'm going to open a different file, but you guys should have that. I needed a different paper size. So now let's look at 4 different types of loadings, and you'll see how the applied load affects the shear and moment diagrams. So here we have a concentrated force, point load in the middle of a beam. right? My reactions, P over 2, P over 2. And because of that discontinuity at my concentrated force, I'm going to break it up into two different sections, right? One before the load and one after the load, if that's my X. So first let's look at X equal to less than or equal to L over 2. Right? It looks like that with P over 2, my shear, and my moment. So, sum of the forces in the y direction. I've got P over 2 acting up, shear acting down. So my shear function for that is P over 2. Take my moment. I've got P over 2 acting at a distance X, right? That's my X. It's acting clockwise, so it's negative, and then acting the other way, positive, m of x. So my moment function is equal to P over 2 times x. Right? And you'll notice, if I take the derivative of the moment function, I get the shear function. Now let's look at my second section, right? This was number 1. Here we have section 2 for L over 2 x to L, right? From L over 2 to L. Now my beam looks like it's got P over 2 and a P. It's got a shear function and a moment function. And can call out some dimensions, right? This would be x. This would be x minus L over 2. Oh, I can move stuff. That's fun. Okay. So, if I take the sum of the forces in the y direction, I get P over 2 acting up minus P acting down, V of x acting down equals 0. Solve for V of x, and I get negative P plus P over 2, so minus P over 2. Take the sum of the moments. I've got minus p over 2 acting at a distance x, right? It's clockwise, so it's negative, plus p times x minus L over 2, right? That's this force. It's acting counterclockwise, so it's positive, and I also have m of x acting positive. If I solve for m of x, I get p, p over 2x minus px minus p times x minus L over 2. If I simplify that, I get negative p over 2x plus pl over 2. So those are my functions. Now let's draw it, right? And let's remember we've got this little right. And what's kind of the middle? Maybe I should get like a straight edge or something. Oh, look at that. Oops. Must have shrank my thing at some point. Oh well. Anyway. We've got, right? Shear is equal to p over 2. And it's equal to that for the entire first section. And then it's equal to negative p over 2. M of x is equal to, right, p over 2 times x. And then minus p over 2 times x plus 2. You'll notice the slope of the shear, right? The slope of the moment, sorry. P over 2 is equal to the shear, right? Slope P over 2, slope minus P over 2. You'll notice that this difference is P over 2 minus negative P over 2. It's P, right? So your change in shear is that, and it's also a discontinuity. We have a discontinuity because we have an applied concentrated force. Shear is constant because we don't have a distributed load. If I look at the area of this, it's equal to P over 2, the height, times the length, L over 2, PL over 4. The value of the moment at the middle is PL over 4. And I go from 0 to PL over 4, so the change in moment is PL over 4 minus 0, right? So it's equal to this area. Similarly, the area here, right, is equal to negative PL over 4. My change in moment is equal to 0 minus PL over 4, right? It decreases from PL over 4 to 0, so it's negative. So it's equal to the area. Shear is constant, so moment has a linear relationship with the length, right? Yeah, we could write linear. Linear, right? So if you have a concentrated force, it causes an immediate discontinuity at your at where the concentrated force is. In this case, it goes from positive to negative, so your shear crosses 0. So you're going to have a maximum at that discontinuity. A maximum in your moment function at that discontinuity. Right? Where my shear is equal to 0. If you remember, that's how you find maximums and minimums in calculus, is you find where the derivative is equal to 0. Right? This also shows that my moment is equal to 0 on either side, because these are a pin and a roller, so I shouldn't have any moment. And my shear, P over 2, is equal to the reaction right at that point. Same on the other side, negative P over 2, equal and opposite of that upward reaction at B. All right. Let's look at a second loading. Now we have a linear distributed load, W. It's constant along the entire length. My support reactions, right? WL over 2 on one side. Sorry. WL over 2 on one side. WL over 2 on the other side. I don't have any changes in load, so I can take the entire beam as one section. I don't have to break it up into 2 like I did with my concentrated force, because I didn't have a discontinuity. So from 0 to L, I have a beam with WL over 2 at the reaction, W acting along it, shear, and sum of the forces in the y direction. Acting up, I have WL over 2. Acting down, I have minus W. Acting over a length X. And then I have my shear acting down. Solve for shear. My shear function is W times X minus WL over 2. No. Got the signs wrong. Minus WX plus WL over 2. If I solve for my moments equal to 0, taking the moment here where I cut my section, I've got let's see, acting clockwise, so it's negative WL over 2 times the distance X, right? It's negative. Acting counterclockwise, so it's positive. I have the resultant of that distributed load, which is WX, and it's acting at a distance X over 2. And then I also have my moment. So if I solve for my moment, I get minus WX squared over 2 plus WL over 2 times X, right? If I took the derivative of that, I would get the shear function. So let's see, let's draw our shear diagram. My shear at x equals 0 is WL over 2, positive. My shear at x equals L would be minus W minus WL over 2. And it's a linear function, right, with a slope being minus W, so need to get my straight edge back in here, because I need the center to be, or the, spoiler alert, I need, right, minus WL over 2. Let's draw a little barrier. All right, those are not together. Right, and then my moment function is a parabola. If you want to plug it into your calculator or into Excel to see what it would look like. Well, let's see. I have a 0 right at the center for my shear function, so I know I'm going to have a maximum right there. So it's going to look like that. It's as close as you're going to get. Right, so let's look again. What can we see? The slope here is negative W. It's a linear function. Right? Where V of x equals 0, M of x is a maximum. Right? If I look at the area under this curve, it is 1/2 base L over 2 times height, WL over 2. I get WL squared over 8. And what is the value of M of x equal to L over 2? I get minus W L squared over 4 times 2 plus W L over 2 times L over 2 minus W L squared over 8 plus W L squared over 4 which is WL squared over 8, right? That's the value of my maximum, which is L over 2. That's where my shear is equal to 0, is L over 2. Get WL squared over 8. It's your maximum moment, right? So my change in moment from 0 to L over 2 is WL squared over 8, right? Matches this area. Similarly, I can find the area on this side, right? Which is 1/2 base L over 2, because it's a triangle, right? L over 2 times negative WL over 2, so I get negative WL squared over 8. And lo and behold, I go from WL squared over 8 back down to 0. So it's equal to that area. Ta-da! So my distributed load means, because it is a constant function, I have a linear relationship between shear and the position, x and x. My shear is a linear function, and then my moment is one step higher. It's a quadratic function with an x squared in it. Okay. Finally, the trickiest of all. Not finally, because we have one more after this. I have a triangular distributed load. Right? this one, let's see, my distributed load, the resultant is 1/2 W times L, right? If I take the area of that triangle, 1/2 the height, which is W, the length, which is L, and it happens at a distance 2/3 of my length. Now this one, I don't know offhand the reactions, so let's solve for them. We might end up needing an extra piece of paper. Write small. So my reaction forces, right? I have my reaction at A and my reaction at B in the Y direction. So let's take the sum of the moments about A in the clockwise direction, which is negative. I have my resultant minus 1/2 WL times 2/3 of my length. Excuse me. And acting counterclockwise, so it's positive. My reaction at B times L. Alright, I can just cancel those L's out. So my reaction at B is, and cancel those 2's. So my reaction at B in the Y direction is 1/3 WL. I can find my reaction at A by taking the sum of the forces in the Y direction. Let's see, acting up, I have my reaction at A and my reaction at B. Acting down, I have 1/2 WL. So my reaction at A is my applied force, 1/2 WL minus 1/3 WL, which is 1/6. Half minus a third is a sixth. Oops. We have, so our reaction forces are 1/6 WL and 1/3 WL. That's just to find my reaction forces. Now let's look at our shear and moment functions. They we don't have any discontinuities. We don't have a load stopping or starting. We don't have any concentrated forces. So we can again just use the entire beam length. This is where I'm going to run out of room. All right, I have my beam, and acting on it is this triangular load. My reaction here is 1/6 WL, V of X, M of X. Here So the applied load, we need to use similar triangles. All right, my applied load is equal to draw it. Right. If my whole load is W over L and my section load has a length X, my applied load at X, W over X, or W of X over the length X is equal to W over L, so W at X is equal to W times X over L, right? It's just proportionate. So my applied load is W times X over L. Right? Let's take the sum of the forces in the y direction. I've got acting up 1/6, WL over 6, right? Acting down, I have 1/2. I'm going to take that triangular load, make a resultant, so 1/2 times WX over L times a distance X, right? The base X, the height WX over L. And I have my shear function. Solve for shear, and you get WL over 6 minus WX squared over 2L. So it's a quadratic relationship, which makes sense because my derivative of my shear should be my loading function, and my loading function is a linear function because it's a triangle. It's not a constant like the previous distributed load. I'm gonna want to know where shear is equal to 0, because that's where I'm going to have a maximum moment. So I might as well do it now. V of X equals 0. WL over 6 minus WX squared over 2L. And you'll find square root 1 over 3L. If you want to do the math yourself, right? Basically take 2 over 6 and take the square root. Alright, solve for X, which is essentially 0.577L. So it's a little over halfway. Not quite 2/3, not quite a half. I'm going to can I select some stuff? Let's see. Yeah. Look at that. Okay. I want you to go like that. Oops. Delete. Okay. So now I'm going to find my moment by taking the sum of moments at the cut section. I've got WL over 6. WL over 6 negative times X. It's causing clockwise moment, so it's negative. My resultant, right, is acting at a distance from the cut section, X over 3. That's the centroid of a triangle. And it's acting counterclockwise, so it's positive. So 1/2 WX over L times X. That's the resultant force. And it's acting at a distance, X over 3. And then I also have my moment function. So if I solve for the moment, I get WX cubed, well, I get WL over 6 times X minus WX cubed over 6 times L, right? 1/3 times 2/3, I get 6. So let's go take a look at our moment function. So WL over 6 times X, WL over 6, I'm going to multiply it by X. WX cubed over 6L, if I take the derivative of that, I would get WX squared over 2L. Yeah, WX squared over 2L minus. Let's see. I knew the moment happens at. What's funny is I'm writing really big. There should be a maximum moment at X equal to square root 1 over 3 times L. So if I want to know what that is, M of X equals square root 1 over 3 L. WL over 6 times square root 1 over 3L minus W L cubed over 6L times, let's see, 1 over 3 times 1 over square root 3. I had this wrong in my notes. Okay. Right. So let's see. Maximum moment is right, okay. This L goes away, this becomes a 2. So that's why we have L squared. Yeah. And make sure of your units too, right? If my W would have foot per length, I need to multiply by 2 L's to get foot pounds for a moment. Right, WL squared times 1/6 square root 1/3. Well, square root of 1 is 0. 1/√3 minus 1/6 times 1/3, 1/square root 3. Is that anything rational? It would be, let me see, what would this be? 1/6 square root 3 times 1 minus 1/3, 1/6 square root 3 times 2/3. 1/9 square root 3. Is that right? Oh goodness. Right. 1/6 times square root 1/3 minus 1/6 times 1/3 times square root 1/3. 1 divided by 9 square root 3. Okay, well, yeah, as long as I was right the first time, that's good. Yeah. Next is WL squared over 9 square root 3. Okay. So, let's draw that. Let's see, my shear function at x equals 0 is WL/6. Right? I know it's going to be 0 at 0.577 L, so somewhere about here maybe? I don't know, here. It's, if you graph it out on your calculator, which is really what I did, I forget the shape of things. Right, it's a negative x squared, so it's an upside down parabola, and it looks like that, right? And it better be equal to WL/3 on this side. WL/6 minus WL/2. Alright, that's negative. Alright, 1/6 minus 1/2 is negative 1/3. And then if I draw my function, right, it needs to be about equal to, it needs to have a maximum right about where that 0 is. something like that. There we go. That doesn't have the right maximum. Okay. See maximum, like that. Something like that. Right? Where shear equals 0, M is maximum. I'm not going to do the area under the curve because that's a lot of calculus. But right, if we do the area under this curve, we should get should be equal to negative WL squared over 9 square root 3. Similarly, the area under here should equal positive WL squared over 9 square root 3. Right, because that's the difference between 0 and this maximum, which is WL squared over 9 square root 3. Again, 0 moments on either side because it's a roller and a pin. This shape, I guess I could comment on that. This shape, right, quadratic, because it's x squared, it's upside down, negative. This is, what's after quadratic? A cubic parabola, right? And notice, right, this is x cubed. And this is all because this function is linear. It's x, right? Take the derivative of the moment, x cubed, you get an x squared function. Take the derivative of an x squared function, the shear, you get the applied load, which is linear. Now, building a shear and moment diagram, you don't have to do this every time. It's just these little functions might help illustrate things or help you draw them better, right? Like I said, where the moment is the maximum has to be where the shear is 0, so it'll tell you where you need to draw the top of that. Especially if you're drawing by hand, you're not, a calculator, so. Okay? That was the hardest one, I promise. The last function we have is just for fun. This isn't even a beam. Let's say we have a beam that's subjected to a concentrated moment. Right? Since I have that concentrated moment, I'm going to have some type of discontinuity. So I'm going to break it up into 2 different sections. 1, 2, I have some moment happening at this side A and some moment happening at this side B, and then a concentrated moment in the middle. So for 0 to L over 2, right, I've got this beam with counterclockwise moment MA, shear function and my moment function. If I take the sum of the forces in the y direction, I figure out that my shear function is 0 because there's no other forces in the y direction. If I take the sum of the moments at my section, counterclockwise positive, I have my negative moment at A plus my moment at X, so my shear function for this segment is equal to my moment at A. It's a constant. Now I'm going to look for my second section, right? I have my moment at A, I have this applied moment, and then I want to look at my shear and moment. Sum of the forces in the y direction. I have my shear is equal to 0 because there's no other forces in the y direction. Sum of my moments about this section. I've got my negative moment at A, my applied moment, which is counterclockwise, so it's positive, and my moment function. So my moment function is equal to my moment at A minus my applied moment, which, if this beam is in equilibrium as a whole, is equal to the reaction of that moment B. Right? So my shear function, I have no shear. Not worrying about shear right now. I have my moment at A, my moment at B, and then right. Oh jeez. You go back. Okay. I'm not a highlighter. You go over there. Okay. I've got. Pretend that's a straight line. Right? It's constant. Oops. I have a constant moment MA. Then I have a constant moment MB. Right? And the difference between the two. My discontinuity is that concentrated moment. Not much else to say. I guess it's negative. Actually, I just drew this wrong. If my moment at A is negative, right? It's acting counterclockwise. Right? And then I have my moment at B. It's acting clockwise, so it's positive. And the difference between the two is that applied concentrated load, right? It's a discontinuity. Okay, so if you want to summarize what we all just talked about, if I have a concentrated force, it's a discontinuity, and it's going to be a big jump in your shear. It's not going to cause a discontinuity in your moment, but it's going to cause a discontinuity in your shear. And beyond that, it's just a linear slope. Because we have a constant. If you have constant shear, then you have a linear slope for your moment. And the maximum occurs where you have zero shear. If you have a linear distributed load, you're going to have a, I guess not a linear distributed load. Let's say it's just a distributed load. Constant, that's the word, constant. So go back and change it. Constant distributed load. Then so then your shear function is linear, right? This is constant, linear, quadratic, x squared. Again, you can use the shear to find the change in moment and find out where the maximum moment occurs. Triangular load, we have now a linearly varying load. So I have an x squared for my shear function and an x cubed for my moment. If I had a parabolically distributed load, then x squared, then my shear would be x cubed, and my moment would be x to the fourth. Right? And finally, my concentrated moment doesn't have any effect on my shear function, but it causes a discontinuity in my moment function. And the change in the moment would be due to that due to that moment. The change would be equal to that. And it could be positive or negative, right? If that was a negative moment being applied, if that was a clockwise moment being applied, it would cause your moment to decrease by m. Your moment function at that point to decrease by m. So that's using shear moment diagrams and basically knowing how different loadings affect them visually and obviously mathematically. But I hope that helped. And next is a shear moment function example that we will do together in the Zoom meeting. Thanks.